Okay. Okay. Thank you everyone for waiting for this. Okay. Today I will talk about our recent work on introducing fractal self-statistics. So this work is done with Nat Wilbur and Mike Hermley. So this is the outline of my talk. First, I will make a brief introduction of fractal physics. Yeah. So in this talk, in this talk, I will focus on gapped fractal phase to be specific. Okay. Compared to gapless system, gapped phases are relatively simple, but they can be highly non-trivial. Famous examples include the Fracton quantum Hall states, which lie within the category of topological phases. Fracton phases are a new class of Fracton, new classes of phases theoretically discovered in the last decade during the study of topological quantum computing. Although sometimes they may also be referred to as fracton topological orders, they have crucial differences from the standard topological orders. For example, their ground state degeneracy has a system size dependence, which is not completely topological. In this talk, I will use topological order for the standard case only, which has a finite ground state degeneracy and finite ground degeneracy and can be described by topological quantum field theory. So here I list the main differences between topological order and fractal order. In topological order, the point-like excitations can be created by string operators and move, and they are free to move. In the fractal order, there's a new type of point-like excitation that must be created in groups of more than 2 excitations and by non-string operators. As a result, they are not free to move without creating multiple excitations, and their ground state degeneracy behaves differently, as we just mentioned. Another difference is in the conventional topological order, the total number of superselection setters is finite, while in the fractal in fractal orders, there are infinitely many superselection sectors. Okay. To be concrete, let's look at several examples. In the topological order, the simplest example is Torre code. So the Torre code can be viewed as a Z2 gate theory, and it is also be used as a stabilizer code in topological quantum computing. So the key properties of it is ground state degeneracy is 4 for any size of systems when it is put it on the torus. So it doesn't depend on system size. Its excitations are created by string operators at their ends, and these excitations are free to move by string operators. In contrast, in the fractal order, a simple example for the fractal order is checkerboard model. It has a very similar Hamiltonian form. So it is also made of both A and B term, A and B terms. But its ground state degeneracy has a sub-extensive dependence on the system size. So it's gapped. And the ground states also cannot be distinguished locally by local measurement. So it's in this aspect is similar to topological order, but it is still not fully topological because its ground state degeneracy depends on the system size. Another crucial aspect of the checkerboard model is it spots the so-called fracton excitations. An example is B excitation. It's easy to check. No local operator can create a single B excitation. For example, when we apply a poly X operator, apply one poly operator, it will flip the 4 B terms, and the B excitations are deconfined. They can be spatial separated and created at the corners of an extended operator, but this operator is not of a string forms. This B excitation is a fracton, means it cannot move without creating more than one excitation. So when it moves, in this case, when it moves, it's split into 3 excitations, and it is immobile in the conventional sense, and the immobility is close related to the fact that the excitation are not created by non-string operator. Another more exotic scenario for fractons was discovered by Haah in 2011. In Haah's code, the Haah's code is also made of A and B terms, and each term is a product of 8 poly operators, but the outcome is really mind-blowing. So in this model, all excitations are fractons. So these excitations can only be created by well-separated excitation can only be created by fractal shift operator like this. Yeah, this. Okay. So we will talk about these examples later. So then I also list a brief history of the fractal model construction. So it starts with the pioneering works of Sherman and Haah, and then the field becomes popular in the condensed matter community by the work of VG, Haah, and Fu. They introduced simpler type fractal models, and they also invented the term fracton and type 1, type 2 fractons, fracton models, fracton physics. And they also shows the duality between subsystem symmetry and fractal order. Which is familiar, which makes the topic more familiar with the condensed matter community. Later, Practical found the high-rank gauge theory description for fractons, and then it follows many other constructions like tuple layer construction, and also constructions on general manifolds, and then non-abelian fractons, and also people try to use topological defect networks to get a more universal way to construct fractons, and use Chern-Simons series to construct fracton models that cannot be that can be chiral or something not can be presented as the stabilizer code. And also people construct hybrid fractal models which also has some features of 3D topological order, like the loop excitations. So I just make I make a partial list of the model construction to show. Right now we have a very big zoo of fractal models, and so the next natural question theoretically is to understand how to classify fractal orders. I think this problem may contains at least two aspects. First, how to distinguish different fractal orders, and the another aspect is to understand how to describe these models in the renormalization group picture. So to understand whether we can define some fixed point for these fractal orders, because this problem is challenging because it looks the lattice structure is really crucial in the long-range entanglement pattern for the fracton phases. Of course, there's also natural questions for to ask about how to realize the fracton phases experimentally, and what about their potential applications and the related problem about phase transitions. Today, I will focus on the characterization problem. So for this, we introduce the notion of fracton self-statistics. There are several direct motivations for this. The first one is in fracton phases, because particles has restricted mobility, so and some type 1 fracton phase also support lyons and planons. And previous studies already shows that some lineons or planons may display fractional statistics, which is crucial for distinguish different fractal orders. However, in the checkerboard model and Haah code, fractons are the elementary excitations, and we constructed several twisted examples, but we cannot distinguish the resulting phases, or I identified those phases with the original untwisted case by examining only the fusion or statistics of mobile particles only. So we have some. So it looks there's something crucial missing in characterize the fracton phase. So it is related. It should be related to fracton self-statistics. However, we investigated the existing literature and found no definition for fracton self-statistics. A main reason for this is people thought it's impossible. It was impossible to define fracton statistics because they are not free to move. Without fracton statistics, there are many. It's very awkward to understand some problem related to about fractons. For example, people may ask whether we can define topological spin for fractons, even we cannot define fracton self-statistics. And many people also asked whether there's a fracton analog of a non-abelian fractons. For the second question, we already have some non-abelian models constructed, but to define non-abelian is we can only use very indirect way to investigate its properties.
Oh, I actually have a naive question. So for topological order, there are two ways to define topological spin. One is just self-statistics, and second is if you couple to the geometry metric, it should couple to the spin connection, and the coefficient is the topological spin. I wonder for fracton, are these two equivalent?
Can you repeat? Sorry.
So when we define topological spin, it is the self-statistics, or another way to test or measure topological spin is coupled with the background geometry metric. And if it carries a topological spin, the quasiparticle should couple with the spin connection, just like something akin to the Van-Z term. So for fracton, is it also true?
But how do you measure it physically? Yeah, I think you are describing some topological theory terms, right?
Yes, so this is how topological spin was defined, and I'm agnostic because for fractons, it's usually defined on lattice and hard to write in a continuum. So whether we can define it in a continuum and couple to the spin connection, that is question. So for fracton, are these two type of definition equivalent?
I'm not quite sure because maybe I can come back to
maybe
later. Okay. So because these technical issues, and we went back to re-examine the initial claim about it's impossible to define fracton self-statistics, and we found this statement is incorrect, and let me explain why. So as a preparation, we first let's review a little about how we define fracton anion statistics. So the statistic is defined by swapping two anions that belongs to the same type. Okay. So and the exchange process can be realized using three moves along three directions, and realize the whole exchange process along a T-shaped path. Okay, so we can inverse the one process to move the red anion to the center, and move along two to the bottom, and then move the blue one to the left, and then the red one to the right. The whole process is like this. And in 1, 2, 3, the three process, we can return the exchange process of the self-statistics as 3 to 1, 3 to 1. And it's notice we know although there's some arbitrariness in choosing the phase for the 1, 2, 3 process, the arbitrariness will be cancelled with the inverse process. So it is clear that the self-statistic is well defined. So since the exchange process is a cyclic process, we can start with any middle step. So for later convenience, we start with a state that one anion is at the center and one is on one side. So we consider in our paper, we really consider analogous process to this exchange process. Okay, so we claim that fractal self-statistics can be defined analogously. So to understand this, there's two main conceptual issues need to be resolved. The first one is how can we move something that is immobile to realize the exchange? And the second one, what should be swapped with a fracton, since by definition of fracton, actually two fractons at different positions cannot be related by a local operator, otherwise it moved from one position to another. So for the first issue, so we noticed that the immobility is we claim that fractons are immobile just in the conventional sense. That means it moves as a whole, but fracton allows a weaker notion of mobility, that's fractional mobility. For example, the 1, 2, 3. I don't know. Yeah, there's some innovation problem. So it's just a 1, 2, 3 process. One fracton can move, but split into 3 excitations here. In the checkerboard model, for example, if we consider a cube excitation at the center, it can move to C1 prime, C1 double prime, and C1 triple prime from the orange one to the red ones, or to the blue ones, or to the blue ones, or to the green ones. So there are 3 directions we can move make a fractional move for a single fracton, and the 3 moves makes a windmill shape in this figure. And this windmill is actually is very similar to the T-shaped path for the mobile particle or anyons, as we discussed earlier. So analogously, we should be able to define some exchange process associated with the windmill. And for the second problem, what should be exchanged? So a fracton, the answer is the fracton should be swapped with configuration of several fractons. That's because a fracton move is split into several into a configuration of several fractons. Fracton is not mobile, so the exchange between 2 fractons is not possible. But in the superselection sector of a fracton, it contains many possible configurations. The exchange should be between 2 configurations within a same superselection sector. In this case, we are exchanging A with 3 fractons, the colored orange here, and make an analogy to the anion exchange process. We get this exchange process. We get the statistics for fractons. Let's look at this in detail. So here, M1, M2, M3 are membrane operators that move the fracton from the center to the 3 directions, while it's split into 3 excitations. So M1 will move. So the whole exchange contains M1, M2, M3, and their inverses. Yeah, I think it should be clear. So first we move fracton A away from the center, and then move the A hat to the bottom, and then move the black fracton back and to the left, and then move the orange fractons to the center. Then this realize the exchange. Then I will. Then let's look at some detailed properties of the fracton self-statistics defined this way. First, it looks there's more than one way to choose the windmill. So there's many possible fracton self-statistics. For anyons, the three directions can only order the clockwise or counterclockwise. So they are only inverse of each other. So there's only one self-statistics there. But for fractons, there are 8 ways to put the three membrane operators. It looks we need 8 self-statistics here, but we notice that inversion-related processes are equivalent. The argument is like this. So we consider 2 windmills that are related by inversion symmetry, related by inversion. There's no symmetry here. Okay, then we can smoothly deform the membrane operators as in the middle figure. Then in this deformation, the part near the origin become exactly the same as the inversion related process. So this shows that theta, the statistics on inversion related windmills are just the equivalent processes. Then we are left with 4 statistics now, and actually there's one more constraint between the statistics. Their multiplication is 1. This identity, to prove this identity, we also to prove this identity. A good way to prove this identity is to study the relation between self-statistics and fracton self-statistics and dipole mutual statistics. By dipole mutual statistics, I mean SAB. It is defined a dipole along the S. So the dipole, there are 3 types of dipole. The dipoles can be lying along the X, Y, or Z directions. So there are 3 dipole mutual statistics here. For example, the XAB is between dipoles along the X directions. And we can show that the product of these 2 self-statistics gives dipole statistic between A and A. So the proof is we can deform the 2 process like B and C, and when we make a composite between the two processes, it is equivalent to breeding A and A bar with A. This process is actually equivalent to SXAA. So this gives a proof here. With this relation, it's easy to show that the identity we just mentioned. So the first two factors gives SXAA, and the last two factors gives SX bar AA, and the later one is just get the gradient and the dipole direction inversed. So it's the inverse the 2S process are just the inverse of each other. So this ends with an identity. We can similarly, we can also show other relations between fracton self-statistic and dipole mutual statistics. Two examples are given here. It's like a double exchange will give a product of mutual statistics and the fusion rule for the self-statistics. They are pretty much the analog of the anion cases. Yeah. And with these identities, we can show that if A satisfies the fusion rule at that A square equals 1, then it's clear that its mutual statistics can only be plus or minus 1. As a result, its self-statistics can only be bosonic, fermionic, or semionic. So they are discrete values. So we can use this self-static. Sorry.
Maybe you can finish that sentence. I will ask something.
Okay, so because the discreteness of the self-statistics, this justify it can be used to distinguish different phases. Yeah. Okay.
Okay, great. Thanks. Very interesting result. Maybe many things. This process is basically done on qubit lattice, right?
Yes. Yes.
So, but do you expect something will be similar for other type of lattices?
That's the point I want to point out. So
okay,
these identities, so these properties are defined. If we are assuming to derive these properties, we are assuming the fractons are foliated. Means it has the mobility like those in the X-cube model or checkerboard model. So yeah, it admits the membrane operators along the XY plane, YZ plane, and ZX plane. Yeah, that's the only exception here. Okay.
So we will limit it to the case you say foliated, or maybe there is some directional XYZ choice.
Yeah, you have three special directions, X, Y, and Z, and you have membrane operators along the XY plane, YZ plane, ZX plane. That's the exception to derive these properties.
So if we do honeycomb lattice but with layers, we can still.
Yeah, if it's that's why I use the foliated fractons instead of type 1 fractons, because in type 1 there are several foliation structures. This is the most elementary foliation structure that support fractons. There may be other foliation structures or higher foliation structure. For example, even the Chema model is not foliated like this. So, yeah. Then this constraint and properties will be changed if the Fourier chain structure is different. Okay. Did I answer your question?
Yes, I think so. At least you helped me. Thank you. Very nice.
Okay.
Let me just ask more because I think that thing is kind of too fast for me. Maybe
Uh-huh.
2 slides back, you said there's some equivalent relation between this M1, M2, M3, or I forget what you define that. Yeah, M1, M2, M3, these operators.
Oh, okay.
That,
Yeah.
to
Okay.
something about inversion. This one I can follow, but something about inversion, I'm not sure what you.
Okay, this one. Okay. Yeah. So this windmill is the inversion of this one, right? Is that clear?
Yes.
And then, for example, the red membrane operator can be deformed like this, right?
Mm-hmm.
And also for the green one and the blue one, right?
Mm-hmm.
Then after the deformation, so the part near the origin, so this part, and this part, exactly is the same as this windmill, right?
Sorry, you mean the second figure the same as the third figure?
Let me see. Yeah, the third figure, but with a cyclic permutation, right?
Okay.
A cyclic permutation, but by a cyclic permutation, so everything is unchanged. So yeah, is that if you switch the color, but the order, yeah.
I'm sorry, I'm not sure. Do you mean the second figure and the third figure? How are they related again?
The second figure and third figure near the origin, they are the same, up to a cyclic permutation, right? If you
sorry, what's the importance of near the origin?
Mhm.
What's the importance of near origin? Why not just the four operators? I'm not sure.
Okay, because let me see. The definition is basically the commutation relations between the three operators, right?
Yes.
So the far end of these operators that doesn't matter to the permutation relation, right?
Mm-hmm.
So that's why yeah, only this part matters.
I see. Okay.
Yeah, that's what about this part? This part is more involved, but yeah, you have to look at the figure for a while.
Okay. Problem.
But the crucial point is there's a simple relation between a double exchange and the dipole mutual statistics. Okay. Then although the probability depends crucially on the mobility of the how the fractional mobility pattern of fractons. The idea of defining fractal self-statistics works in general. It doesn't depend on. I think it is definable for all fractons. So, for example, we also studied the self-statistics for fractons in the Haah code. In the Haah code, the A term and B term excitations. A excitation, for example, the A excitation allows fractional mobility along the three directions by fractal operators shown in the middle figure. So we have three directions, and they make some kind of windmill. So we can define the statistics with the three fractional moves. Okay, but the properties of the statistics will change due to the change of the mobility structure. So in this case, the A and the A term excitation and B term excitation can only be fermionic or bosonic, but the composite particle has a different mobility, and it can be fractional. Okay. Then there's some people drawing on the screen.
Yeah, so please erase it. You can see the message. Please erase it yourself. Thank you.
Okay.
If you don't erase it, then
okay.
actually, let me see. I don't know what.
Is it possible?
I think there's another way. Maybe you reshare the screen again. But just who write it, please erase it. We are doing a serious seminar. Please don't do this type of thing, okay? Please erase it. You may need to unsure and ensure again. Maybe that will work.
Okay.
Okay. Did you hear me? Who wrote this?
Yes.
Please erase it. Otherwise, I will kick you out. Please erase it. Please erase everything you write. Can you unsure how?
Okay, let me see.
Share the screen and share again. Unsure and share again. Yeah.
Okay.
By the way, if people do that again, I'll kick you out and block you. Just to. This is the warning. Please don't do that. Yeah.
Am I sharing?
Yes. Perfect. Thank you.
Okay. Then we can look at some applications of the Fracton statistics. So first, it helps us to distinguish the Fracton twisted checkerboard models. The model the twisted check models are analogs of the twisted gauge models for topological orders. So the twisted gauge models are Hamiltonian formulation of the derivative topological field theory. So in our paper, we define we make a formulation that based on this triangulation, and here we add a host to the triangulation to make to get a non-poly stabilizer formulation such that the AB term commute and the AB term all square to 1. As a result, we can analyze all the full spectrum. The full spectrum completely analogous to the toric code case, and we can, for example, we can define the twisted bit flip operator to excite the B excitations. And the twisted checkerboard model use similar constructions along each layer of the system. So the twisting construction can be along the x edges as in figure B, and along the y edges as in figure C, or it's also possible to make the twisting construction along the x edges. The model was originally proposed in our paper, our PRB paper in 2019, and in our new paper we also make a non-Pauli stabilizer formulation for us in order to get a simpler, in order to make a simplification for analyzation. Okay, because the twisting can be along 3 directions, so we get 7 twisted models. They are all semionic analogs of the original checkerboard model. In our twisted fractal model paper, we wasn't able to distinguish or identify the resulting phases from the untwisted case. Now the problem can be resolved by using Fracton self-statistics. First, in the original checkerboard model, all excitations must have either fermionic or bosonic statistics, because their fractional moves are realized by product of Pauli operators, and Pauli operators can only commute or anti-commute with each other. In the next, we consider the twisted case when we with the twisted construction along one direction. In this model, we found that the B excitation have a semionic self-statistics. So this already distinguished the phases of the 2 models. But moreover, we also find that we also double-checked that only fermionic or semionic mobile particles only allows fermionic or bosonic statistics. As we found in an earlier paper, and it is the reason why we didn't distinguish the phases of the 2 models earlier. And these facts can also be checked by the identity we just showed about how the fusion rule for the self-statistics. Because any mobile particle must contains even number of B excitations, and so their self-statistics, their semionic self-statistics will cancel each other, and the mutual it's easy to see mutual statistics is always plus or minus 1. So any mobile particles only have ordinary statistics. These facts further confirm that this model presents a new fractal order. We call it semionic fractal order. It cannot be a direct tensor product between untwisted fractal order plus 2D semion systems. Because in the direct product of the in the direct product case, it's obvious has mobile semionic particles. That's not the case in this model. Further, we can also consider the case with 2 twistings. Now the B excited, and because the twisting in two directions may cause causes a cancellation and resulting no resulting no semionic behavior anymore. Further, the mixed statistics can be completely cancelled by combining some A excitation to the B excitation. Then we get a perfect match between excitations and in the untwisted case and the doubly twisted case. This suggests that these two models actually belong to the same Fracton phase. Indeed, this is the case. We explicitly find a local unitary transformation that relate the ground state between the two models. So, and similarly, we can use these tools and the tools of self-statistics and the similar construction of local unitary transformations and proof the 8 models belongs to 2 Fracton phases. One is the untwisted case, the other is a semionic Fracton order. Another application of Fracton self-statistics is to study. Okay, right. Do you have a question?
Let me see. I guess.
Mm-hmm.
Yeah, I'll just ask question, but not sure the ordering. Can you go back slides? Let's see. Mm-hmm. Maybe start with the earlier when you say that you have a general statement about the self-statistics defined by some lattice vector, right? Mu, direction, etc. Right? Earlier, there's some definition. Yes. And then you say that it requires to be layers of abelian fracton. Is it? You have some condition on abelian, something like that, I guess.
Yes.
Abelian
Fourier. Yeah. I need okay. I make this assumption to make, for example, proof this is identities, because if this is an operator equation, then it's not necessarily only a phase. It can be diagonalized that contains phases like this, right? If it's a matrix, then it's not just a phase. It's a in general, it can be a matrix that can be diagonalized into, has diagonal elements like this, right? So
let me make sure. So usually in the usual topological order, the T matrix can be diagonalized in the proper basis, right?
Yes.
Here, are you saying that for Fracton, it's not obvious for the analogous maybe T matrix, which captures some topological spin? You may not know whether this diagonalization makes sense. Are you trying to say that, or so? The criteria for abelian here actually is. Do you mean?
Yeah, for I think most of the equations hold even it's non-abelian, but you should read them as a operator equation or matrix equations for matrices. And
is there any non-abelian example?
I didn't discuss any non-abelian example in the application, but I think it can be easily generalized to that.
But no explicit example yet.
No explicit example yet. But for example, this proves it holds for S. Actually, it can be read as a identity for self-statistics operator if it's non-abelian, right? Yeah. In general, there are matrices, and there may be some subtleties when it's non-abelian, because when it's a non-abelian, you have to distinguish topological spin and statistics. Topological spin is only a quantum trace of self-statistics. So I think these equations are hold as an operator equation, but I'm not sure whether they still hold for topological spins. I think that's my current understanding.
Oh, so by the way, so what's exactly the set of data that will label the statistics for the type of a fractal order? Like what are exactly the independent data? Like
Independent data.
For example, like a 2+1D topological order, you will need modular S, modular T, and maybe chiral central charge, right? Maybe.
Yeah, that's a good question. But
here how do I know which one is independent?
Yeah, how to make a complete list of statistics, right? You want to classify all the statistical behaviors, right?
It is the data you know so far. So there's a modular S, modular T, and chiral central charge for 2+1D bosonic topology. So how about here?
We haven't give a complete thorough study on that aspect.
But you will be able to determine already this theta defined can at most to be plus minus I, the fractional value.
Yes. But this is just a constraint on one quantity, right? But I think you are asking how to give a set of data such that all statistical process can be are expressible in terms of those data, right?
But you don't need to think too far from like something you don't know. It's like just within the braiding process or the exchange, whatever the moving, there's operators that you consider. What are the data like? There are so many, but if you want to choose like a minimum one, what are the minimum set? Just within the context you explore on other.
Yeah. For the answer is we didn't classify all the mutual statistics processes. So for self statistics, we know that there's only 3 independent ones. If we don't consider mutual statistics, that yeah.
And how about those S are derivable from theta? Is it the S?
Yeah, the S can be. Yeah, S can be. Yeah, the problem is whether we can be. I don't think it's possible to determine all the mutual statistics from self statistics only. I guess there are some extra information contents in the mutual statistics, and so in the current work we focus on only on self statistics. So we don't have, the short answer is we don't have a complete story for mutual statistics. That's that's.
Don't worry, but just for whatever you already have. So you will say self statistics you can determine by three of the theta, and subject to, and everything else are just derivable from this 3 of the theta.
Yes.
Some choice of X, Y, Z, and bar.
Yeah, at least for this mutual statistics, it can be determined.
But let me just ask one more time. That you say there's a foliated abelian foliated that statement. Does it change does it affect the theta quantum number? If these are not abelian foliated, will they change the theta to be not plus minus I, plus minus 1, or can it be more fractional or something different than that?
If it's a non-abelian, then I think they are matrices first, and the matrices can be diagonalized, and the diagonal its eigenvalue can only take value plus minus 1 or plus minus I. That's the statement.
I see. Thank you very much.
Okay.
Thank you.
The final application is is about the twisted variant of the Haah code. So we know that the 3D Torah code has a variant spin model where fermionic quasiparticle emerges. So there's an analogous
I'm sorry
case.
again. Sorry, because you are switching the slide. Can you go back one? I'm sorry. Yes, this one. What's the? I think every Hamiltonian is written, but how about the button HXYZ? HXYZ What's this?
Oh, okay. So this one, yeah.
XYZ. Sorry, I maybe missed somewhere.
Yeah. So let me see. So there's a twist. So along each layer of the checkerboard model, there's a twisting construction similar to the 2D double semionic model or the twisted gauge theory. But the twisting depends on the this the x twisting is along x edges means the twisting is made along the YZ plane, YZ layers. So YZ layers, and the twisting factor depends on the x edges. So the product of the two z values on the two spins. So the construction is associated with the x edges in this model, and the twisting can also be made along the y edges. So that's why that's why we can also have HYCB checkerboard, and we can make the two twisting construction together along both the x edges and the y edges. So that twisting will gives HXYCB here. That's a model with twisting construction along two directions. Is that clear?
So XYZ will be along maybe something like 111 direction. I'm asking the last one because
the last one, this one.
H checkerboard XYZ.
XYZ. That's twisting is along. We make three twisting. Three twisting factors are added to the A operator. The three factors are associated with x edges, y edges, and z edges, respectively.
Yeah, that's fine. Thank you very much.
Okay. So the final example is about the twisted Haah code. So there's an analogous variant for Haah code. So that's given by in this paper, and we are expecting that the A excitation as a charge excitation will become fermionic. But so using now we have the notion of Fracton statistics, we can show explicitly that each A excitation indeed becomes fermionic, and this can be used to distinguish the phases of the variant from its untwisted cousin. Yeah, so some more careful readers may ask whether it's possible to compensate the statistic change by attaching B excitations to the A excitation, like in the Torre code or in the checkerboard model. We discovered here similar behavior here. So, but in the Haah code and its twisted version, this attaching operation does not work because it will change the mobility of A excitation. We notice that the A excitation and B excitation has different mobilities. Their mobilities are related by an inversion operation, and when we combine A and B excitation together, the composite excitation has a more restricted mobility. So, for example, both A and B excitation can have a windmill within the YZ plane, but the composite particle doesn't allow such a planar windmill. It can only its self statistics can only be defined on a windmill like this. It uses all the three directions. Okay, so the statistics of A excitation indeed distinguish the two phases between the model, the twisted model, and its original version. Okay. Okay, that's the summary of my talk. I make a brief introduction of fractal physics, and I also discuss about our work on fracton self-statistics, about its motivation, definition, properties, and applications. Okay, thank you for your attention.
Thank you very much. Thank you, Haah, for very wonderful result and talk. Any question from the audience? Please feel free. I do have, but I think people should ask first. Yeah, maybe let me ask first. Let me know what I will ask. Go back a bit. Let's see where I will try to ask. Oh yes, this one. So say the A excitation will be fermionic for this variant of Haah's code, is it? A excitation will be fermionic?
Yes.
For this some variant version of the Haah's code. Is it? Variant, just what you write in the title. Variant of Haah's
it's a variant, autistic variant. Okay. Yeah, it's a modified Haah code or something. Yeah.
We know, so these are the self statistics is fermionic, is it? And are there semionic type as well?
No, there's no semionic type, because with this kind of mobility, fractional mobility, I can prove that A and B must be plus or minus 1. A excitation, B excitation can only be fermionic or bosonic, I think. Yeah, but yeah. For the neutral for the composite particle, I'm not sure, but yeah.
So how can that be fractional in which value? The theta AB.
Theta AB, it can be a fractional value, yeah, because
fractional in which, like a plus minus I, or even more fractional?
Yeah, it can be more fractional because it's a composite particle, so it should have a it should equals to theta A times theta B times some mutual statistics between A and B, right? And the mutual statistic between A and B can be fractional in general. That will give the more fractional statistic for the composite part.
How fractional it can be?
It can be, I think it can be any root of any root of 1.
Oh, I see. I see. You mean like
Like
yeah,
and any root like I plus minus I, or even the square root of I, etc. Yeah.
Oh, I see. I see. This is confirmed result. You just guess, so I'm not sure.
Oh, I know the examples. Like you think about the n version of the Haah code, then it will have such fractional statistics.
Thank you. But I think earlier you said A has become fermionic, but how about, is there also further constraint the choice of B type of statistics then? If A is fermionic, how about B? Can you choose either to be bosonic, fermionic?
I thought about that question, but I don't know the answer. Yeah, yeah. I feel maybe it's not possible. Yeah, the problem is we have this model that we try to resolve the problem of distinguish the two phases. But we don't know other models that both A and B can be fermionic. That will be a very interesting question, and I don't know the answer.
Do you know whether those theory or this type of fracton phases with fermionic versus bosonic statistic for A or B, do they correspond to certain anomalies?
I guess there may be some anomalies associated, but that's a very interesting direction for the future, and we haven't go that far.
No problem. Thank you very much. I don't know whether it's still wrong. I think I was
maybe I could comment that if A and B are both fermionic, somehow that should be anomalous, right? So it would be interesting to see if there's an obstruction to that and how to quantify that with anomaly.
Do you know whether it's anomalous or not?
Well, I mean, we don't even know how to define the anomaly properly for this yet, right? So
yes.
But we expect there should be an anomaly, but
actually we tried to construct some models like this, but we didn't succeed. So we expect it's anomalous.
Thank you. Very nice. I guess there's some comment Easy make, but probably Easy is not here. I think Nate can help. So I think Easy was asking the topological spin in the usual topological order. You can use the statistic, either the exchange statistic for the identical particle or the self statistics of the same particle, just rotate itself. But that structure is related to the framing of the quasi-particle excitations, and that thing has something to do with how to let me see what's it's actually related to the large classification of a large transformation for general coordinates. It's like a field bind if you put it in a manifold, and that thing is labeled by something related to central charge, chiral central charge, leaving if there's a boundary modes, right? Then there could be some gap-age modes, and that type of quantity you can characterize by chiral central charge. So this thing is like a related, the the statistics that you are doing here somehow is related to the underlying the field theory TQFT that you put on the manifold. And so I guess Izzy was asking that is there some understanding from maybe from the manifold side? I think that statement probably is not necessary, to be true or clear for the fracton system, but I guess Izzy was asking that, and maybe I don't know whether Net or Haah has any comments on that. Yeah, or do I
only have speculations at this point.
Do I say something makes sense at all? Yeah, I don't know. I think anyway, yeah, it's not clear to me.
Yeah, maybe you could have framing on each foliation, yeah, but I don't really know too much.
Yeah, but then I think a related question is that is there some notion of a chiral central charge of the? Well, that's a bit tricky because these are 3+1D, right? So yeah, I don't even know. Let's see. Is there a quantity that you can kind of try to observe on the boundary of this 3+1D bulk theory? That may be something.
I think there are some papers that construct like fracton models by like gluing together like chiral stuff, right? But
Yeah,
but
like
yeah.
like let's see. Yeah, like the Chern-Simons construction.
So then the 3+1D series somehow is viewed as some layers of a 2+1D, and there are some chiral central charge for each layers.
Right. And then there are also higher foliated versions too in the literature, I think.
Yeah.
Okay, thank you.
Maybe each question maybe formulated, is there a topological response theory for the topological spin or self-statistics?
Yeah, well, I guess probably more related to the underlying tree. Yeah, it's probably not something. Yeah, it's probably not something on the latest. It's more like the structure, how you put on manifold, that type of things. It's like you put a coordinate. Usually you have a manifold and you have some local frame, right? And then you put a field bind, and then you can do general coordinate transformations, and you can detect some distinct class. And yeah, those things are related to this framing number. Yeah, anyway. By the way, audience, please feel free to interact, ask question, and we can start recording if that's. Yeah, any other question, comments? Start recording then. Any other question, comment?